Hi, I'm Anurag, and I have with me Gilad. So we will be talking about something that actually relates quite well with the conversation that we just heard from Sabrina. That, okay, so we need all these really nice gates so that we can do all these fantastic algorithms that provide us true quantum value, quantum advantage. But if you are in the lab, you still realize that getting these really nice gates can be quite a challenge. So we'll look at a concrete example of what this means for specifically superconducting qubit systems, where if you have a tunable device, it's pretty standard to work with these flux-based gates, where you tune the flux and the coupler on the flux and the qubit to get good 2-qubit gates. So we'll be looking at this picture on the right throughout the presentation. What we see on the top left is often what most experimental scientists in the lab see when they are trying to calibrate a 2-qubit gate. It looks very distorted, very asymmetrical, and what they really want is the bottom right picture, which is, really clean, smooth, symmetrical. So we want to understand how do you get from the top right, the top left, to the bottom right picture, and how do you do it in a way that is fast, seamless, and efficient. And we believe that you need 3 ingredients to get this done adequately, efficiently. So you need a good control stack, you need software that works very well with that control stack, and you need software that is very good at modeling and predicting the behavior of quantum hardware. So we'll talk first about the control stack, and that's where Gilad will take over.
Great, thank you. So let me tell you briefly about Quantum Machines. We're a company that specializes in the control stack, as Anurag said. We are headquartered in Israel, but a global company. Over 300 customers across 20 different countries. We're over 180 people today. And if I show a little bit about the breadth of the products you see on your left, the room temperature control electronics, I'll tell you a little bit more about that shortly on the next page. On the right, you see our cryogenic components. I won't tell you about that right now, but please come by our booth if you'd like to learn more. So our flagship product is the OPX1000, is control electronics. For those new to the field, this is the box that sits between your laptop and the actual QPU. It's what will take your actual quantum algorithm and execute it as a set of pulses on the actual processor. It is extremely scalable. It can support up to about 1,000 qubits. It is compatible with almost any qubit modality. It is scalable, data center ready, easy to use. And again, please stop by our booth or come by the talk tomorrow morning to learn more about this. I want to tell you specifically as well about a project that the Quantum Machines has been working on together with the Israeli government to build and manage the Israeli Quantum Computing Center. This is on the campus of the University of Tel Aviv. It is a set of on-premise quantum computers as well as on-site HPC available to users. It has multiple processors as well as a testbed system. So what does that mean? It's an entire computing environment. You can see from the top that there are multiple layers at which you can program. We have a cloud layer for integration. We have on-prem HPC. And then in particular at the bottom, you can see that we have superconducting qubits. There are several Quantware devices there. We have photonic system from Orca. And then we have another system available for different projects, for rent, etc. And I'll tell you a little bit more about that in a second. First, I want to also call out the DGX Quantum. The DGX Quantum is our joint work with NVIDIA. It is a sub-4 microsecond round-trip latency integration between the OPX1000 and an NVIDIA Grace Hopper server. If you're interested, please stay in your seats because shortly Michaela will be telling you a lot more about that. Coming back to the testbed system, last summer we were fortunate enough to receive a Rigetti Novera 9-qubit superconducting qubit device that we installed in this testbed fridge, and we invited friends to come and show off what they can do with as far as automated calibration and bring up. And so we were very fortunate to have our friends at Quantum Elements and at Qruise come and really show off what they can do, and shortly Anurag will tell you a lot more about the results they were able to generate on this system. With that, Anurag, it's back to you.
Yeah. So we heard what really good control hardware looks like. So I'll tell you a bit more about what the software side of the story looks like when you're trying to get really good gates for your system. So we are Qruise. We are a software company headquartered in Germany with a team spread all over Europe. We are relatively new and small. It's roughly 3 years old, 22 people. And we develop this software for all platforms. I'm talking today about superconducting qubits, but we work across the stack for superconducting qubits, Rydberg atoms, ion traps, NV centers, and spin qubits. And as you can see, we work very closely with a lot of academic and industry groups throughout the broader European quantum ecosystem. So let's talk about what you can do with tightly integrated hardware and software. The first building block in this software story is Qruise OS, which is our automated calibration software. So you can use it for essentially, once you cool down your superconducting qubit device to the point where you need 2 qubit gates, you just let the software run, and it takes care of all the automation required for calibrating the device, characterizing the different performance points, and so on and so forth. That's the ideal world. We also understand that most often when you are in the lab, your device will not work this smoothly, no matter who tells you what about under 10 minutes, under 5 minutes. If you are in the lab like I am, you know that often that does not happen. So we also provide a lot of tools that actually help you debug and understand your quantum computer the same way you would for your classical device, to understand essentially physically debugging the device and figuring out what might be going wrong. So that's what Qruise OS is designed to do. And we used this, like Gilad mentioned, at the IQCC last summer, and we had some fantastic time working with the Rigetti device. It was a very well-integrated system at the IQCC with the entire hardware and classical and quantum hardware stack. We got some very good times when it comes to calibrating the full chip. So this is a tunable qubit tunable coupler device, essentially, which means that even though you only have 9 qubits, all the couplers are also transpond devices, and you can tune all of these devices, which means you really have a lot of knobs that you need to correctly park in the right places to get very good single qubit and 2 qubit performance. We were able to do that in under 15 minutes and also efficiently park all of the qubits in a place where they are experiencing least amount of crosstalk. And this is all parallelized. We again use the fantastic firmware that Quantum Machines provides with their control stack to easily run these experiments at the same time on all of the qubits. And which is where software really comes into the picture, is that you want modeling and simulation, which is the other part of the story when you're doing calibration, to live very close to your calibration software. And this is again possible because of the tight integration between the Quantum Machines hardware and firmware and the Qruise software. So on the right, you can see some examples of data that is collected from the experiment. That's the left column, and the data that is collected from the simulation. So because we have this tight integration, you can instantly generate what any experiment that you run on the hardware would look like if you were to run it on a simulation. This works as a great sanity check, because at any given point, you can quickly check, okay, is my experiment actually doing what I expect it to do, or am I running something gibberish? And similarly, you can use it to identify good operating points. You can tweak the simulation and use that to do some mock test, do some dry run before actually running things on the hardware. And all of this is possible because we provide a digital twin that I'll talk about more, which can do this kind of comprehensive modeling. We also provide a lot of experiment management tools, which again, anybody who has ever been in a lab knows how difficult it is to manage experiments when you're running them on several devices, running them every day, trying to write a paper at the same time. So these are this kind of quality of life improvements that the software provides for anybody in the lab. So what can you actually do with this digital twin? That's the third part of the story. So we saw what good hardware can do. We saw what good hardware and software integration can do. Now, if you go one step beyond and really want to see what happens when you let software loose on data, what can that do? So this is where Qruise ML comes into the story. We provide a differentiable digital twin. A digital twin is essentially business speak for a model of the whole quantum computing device. So it's not just the QPU, but all of the accessories around it, the classical control stack, the cabling, the cryogenics, everything that can possibly have an effect on the performance of your device. So we developed this digital twin, and then on top of that, this is a digital twin which is differentiable. What that means is, even though this is a digital twin that you write using first principles physics model, so you essentially have a Lindbladian of the system under the hood, you can learn parameters of this Lindbladian from actual experiment data. This is what a differentiability lets you achieve. It comes from the field of machine learning, where this has essentially powered the whole growth of machine learning over the last decade. And then once you have a digital twin that you can learn from data, that means that this is no longer just a model for your theory friends to write on their paper. It's a model that can actually make predictions which match very closely what you see on your hardware. And these predictions are what we call an error budget, because it lets you understand that, okay, if my 2-qubit gate is currently at, I don't know, 99.1%, where is that 0.9% going? So that's exactly what this error budget can do. It can tell you that, okay, out of that 0.9%, 50% of it is because your gates are T1 limited. And another, out of the remaining 50%, you are dealing with a lot of distortions in the cabling. You are dealing with fluctuations in the fridge temperature, things like that. Okay, so let's take a concrete example, which is, this is basically the system that we are dealing with for the plot that I showed in the first slide with these chevrons that were distorted. We have a very typical superconducting qubit system, everything tunable, and we are trying to do this flux-based gate that you see at the bottom right. Again, very standard for any superconducting qubit system. So like I said, this is what you often get on your hardware in the lab, and this is what you want to get ideally. And we want to understand that how do you go from this experiment data looking so dirty and distorted to getting experiment data that actually looks this nice? Well, the answer is through learning, because I mean, we have seen over the last decade that the answer to everything is to just throw learning at it. So we'll also use learning here. We'll try to learn from the experiment data and reproduce how this can see exactly like we're seeing in the hardware. So the way to learn is, like I said, you have a digital twin that is differentiable, but what do you do after that? You feed it a lot of data. In this case, it would be basically the data that we just saw, which is that distorted chevron, the data from that experiment. And then you define some kind of fidelity metric that, okay, I want my experimental data to be exactly replicating what I see in the simulation. And then once you optimize or learn parameters of the digital twin, you can keep iterating until you produce a digital twin that exactly reproduces what you see on the experiment. This is what I described is essentially any machine learning algorithm that you have right now, just that we're using a physics-based model here. And this can give you new insights. In this case, we learned parameters not just about the qubit, but also about the coupler, about the coupling between the qubit and the coupler, crosstalk between the systems, as well as parameters of the control stack. So transfer function. So you have this cabling, and you want to understand what kind of distortion is taking place when the signal goes from the classical control stack all the way to the cryogenics into the final chip. So learning is good, but what can you do with learning? So after you actually finish the learning, now you see that your chevrons look like this. So they don't look these ideal ones anymore, because you have figured out how to produce from the simulation experimental, you have learned how to produce data from the simulations which look exactly as you see in the real hardware. So you no longer have a digital twin that is just modeling an ideal situation. You have a digital twin that is modeling reality as you see it in the field. What can you do with it? You can essentially use it to improve the gate performance. And when I say improve the gate performance, I'm talking about performance improvements up to 50%. So we essentially are looking at a swap gate or a CZ gate, and you can see that before we fixed the gate, or before we fixed these chevrons, we only were getting this blue line, which is not giving you the full contrast. You want it to go all the way to the one state before it comes back. And after you fix the gate by using this learning process and applying the learnings to your pulse so that you can have a pulse that accounts for all of these distortions, you get a very nice gate that has a full contrast. But now you might tell me that, okay, you just throw a lot of parameters at data and you fit it to the data. You can fit anything to any data like that in that manner. So the way to judge the power of any model is to look at how good it is at predicting new physics or predicting new behavior on data or systems that it has not seen before. So we did that. In this case, we went ahead and took a different pulse shape, in this case a bipolar flux pulse, again a slightly more sophisticated 2-qubit gate that gives you better fidelities. And we wanted to see if the digital twin can directly reproduce what it is seeing on the hardware. So what you see on the top left is experimental data. What you see on the top right is the ideal simulation. But in this case, because our digital twin has already learned parameters of the system, without having fed any further data, and as soon as you ask it, okay, if I give you this particular pulse, tell me what the experiment will look like, it was able to produce this data, which looks, as you can see, 98% close to what you see on the left. So this particular data, this was produced from a digital twin without giving it any further learning process, nothing. It is completely unseen behavior. So this is great because now we can use this for fixing new experiments. So we learn once and fix several times. That's the goal, right? We don't want to learn every time. We want to learn only once. So now we fix it, and then we can get, again, a lot of performance improvements. In this case, up to 10 to 15% performance improvements. So bottom line, you can use a small set of data, use it to learn a very accurate digital twin, because this is a physics-based model and not a neural network, so it is not data hungry like your typical neural network. And then once you learn a very accurate digital twin, it can predict system behavior, and by predicting system behavior, it can tell you how to improve your other operations, your other gates, as well as understand what was causing this performance bottlenecks in the first place. Okay, so we have shown you why good control stack is very critical for getting high qubit performance, and we have shown you why not just good control stack, but you need control stack that's very well integrated with the software is essential for calibration and characterization. And most importantly, the one message I want you to take home today is that it's very important to have powerful simulation and modeling tools, because only with good simulation and modeling tools can you accurately understand what kind of performance bottlenecks your devices are facing. And I think with that, we can take some questions.